So we're at moorhen.org, moorhen.org. Structure equals function, structure dictates function. That is why we care so much about understanding the positioning of things at the atomic level. For our specific protein today, it's a cyclin-dependent kinase and inhibitor molecule inhibiting it, and we are trying to see how exactly it is inhibiting or interacting at that surface. So we're just going to go over here, File, Load tutorial data, tutorial 1, say OK. And then right off the bat, we see a lot of things. First, we see a bunch of models. This is the model that we're trying to build. And then the blue netting, that's electron density data from the experiment. And then the green and red are the difference maps. Essentially, we're trying to build the model so that we can explain all the green parts and we can remove the red parts so that the model matches as much as possible to the blue experimental. And the blue experimental is also known as the 2FO minus FC map, and the difference map, the red and green map, also is known as the FO minus FC map. So what we can do right off the bat, besides, is to start interacting with the model. We can just click and drag left and right, click and drag top to left. We can shift and then move like so, and then we can also alt and then zoom in like so. If we want to pan, we can do shift alt, pan like this. And then if we want to scroll in, scroll out, we can also do control, scroll through the electron density. Right now, we can just keep it at around 0.58, 0.5 something. Okay, so now that we have this, where exactly does the protein start? We can simply go to sequence and then go all the way to the left and go to methionine. So these are all single letter representatives of different amino acids. There are generally around 20 natural amino acids, and so this is the sequence. We'll just click into here. This is basically the first amino acid. It's also called methionine. And to the right over here in this little area, we see MET. We're also representing methionine. So we can click on that. And if we want to advance forward, we just simply press space. Now we're at glutamic acid. And we'll press another space. Now we're at asparagine. And so if we are just moving forward, right, we see a pattern here. It's always this blue, then this beige color, and then the beige plus red, and then blue, beige, beige plus red, blue, beige, beige plus red. This blue is the nitrogen. This first beige is the C alpha because it's the carbon where the chain comes off, right? This is always the chain that comes off. It always comes off at C alpha. And then C prime, which is the carbon that's connected to double bonded to the oxygen. NC alpha C prime, NC alpha C prime. And as long as you're going in the NC alpha C prime direction, then you are going down the protein sequence. So as we advance some more, we see that the sequence is now at 16, residue 16, now it's at residue 17, now it's at residue 18, residue 19. So say if we want to go back, we can just simply press shift space, now we're back at 18, shift space again, now we're back at 17, shift space again, now we're back at 16, shift space again, now we're back at 15. Okay, so now we have these basics down. How do we actually make the model fit the data best? Just take a look at validation, Ramachandran plot. Okay, so there's a couple of dots over here. Blue dots are good, red dots are bad. So if we just hover over this red dot and then double click on that, it will bring us directly to this location. We see, okay, there's some green areas here, some green areas over there. How do we fix this? How do we make the model occupy the green area? So here's something else that can sort of help us. Ramachandran balls. Something that is red definitely means it's not great. This is pointed upwards, whereas the actual green part it should be sticking into is downwards. So let's just flip this peptide. There we go. This has turned green. Well, originally it was green. And then this has definitely turned more green. But actually, there seems to be another issue over here. Let's shift down a little and shift down a little more. We see that this is pointing in the opposite direction. Let's fix that. Okay, that is actually significantly better. So far, so good. Validation, let's check the others. Okay, another red dot. Okay, oh yeah, that's definitely clearly in the wrong direction. Let's go ahead and fix that. There we go. This one's also in the wrong direction. Let's fix that. There we go. And oh, hey, look, there's actually something over here. This is not as part of the backbone. This is from shooting off the C alpha, a side chain residue. So if there's something over here and it's connected to that residue, it's clear that this is coming off from the NC alpha C prime. The backbone seems to be fine. It's just this side chain that's messed up. There's a big green blob here. And it's not explained by the model. So let's just go ahead and mutate this residue into another residue called phenylalanine, PHE phenylalanine. And now it goes in. which is great. That's really good. Okay, so let's go and check the other validations. Okay, so all of the backbone issues are fixed, and we can continue on with more fixing. Before we do that, wouldn't it be great so that we can see the updates in the green and the red? Let's find the way. Connect molecular map for updating, and we say click yes. And here we go. We want to have the R factor and the R free as low as possible, usually 0.2 or lower, and then to encourage ourselves, we can get Moorhen points while we're fixing the model. But you can see the green went away because the model now perfectly explains the electron density that was there previously. So we'll just go to validation, difference map peaks. This is going to map out that green and versus the red area. So we have a lot of extra green space all over here. Let's just start by going here. Backbone, no problem at all. But then the side chain comes off, and then there's this big blob. Let's just go ahead and mutate this residue into tryptophan. So this is also another reason why we want to know our amino acids well, so we can recognize them. And yeah, so it perfectly explained the green area, and we got additional Moorhen points. So let's keep on going. Okay, that's just a regular blob. It might just be like a water molecule location. But yeah, but you see this red space where this model is poking out, and the red space is saying, hey, there's not supposed to be electron density here, but the model is claiming there is. And the green space saying, hey, there is electron density experimentally here, but there is no model to explain it. So let's just go ahead and say auto-fit rotamer. And there you go, it's all fixed now. And let's go over here, another water molecule. You see this big gigantic blob? That's most likely the ligand/inhibitor. Another water molecule. Yeah, this one's a good one. We can also do the rotating over here. There we go, significantly better. You just go around trying to fix as much of the issues as possible. You know? Oh yeah, like this one. This is a good one. See how this model is taking up space over here where the blue electron density map actually is not present, and then the software is saying, hey, there shouldn't be any model here. And then we see over here this green space where the software is saying, hey, there should be model here, but we don't actually see any, or there's no model present to explain the blue electron density. So over here you just say auto-fit rotamer, and there we go. Remove the red and then also fix the green as well. It's really, really good. Okay, we can continue onwards. Some of these will be more challenging to do, but this entire place is filled with a lot of locations where water should just be filled in. So we can just go ahead and say calculate add waters and add waters to all the locations. Now it's going to be significantly easier to deal with the validation with much less to worry about. And also as part of this, we can do control and then scroll up a little until it's level 0.62. This will make it clearer as to where everything is and how we want to fix stuff. Okay, let's actually start over here. So this is the blob where the inhibitor is. We can go back to that later. That might be water molecule. Maybe, maybe not, or maybe just be a sulfate ion. Trying to find additional locations where. Okay, so this clearly it might just be like a tyrosine. Let's go tyrosine. Could be. Okay, so it actually said it may or may not be. Since that is the case, let's move that back. Also, we can also obtain something else that can help us. Contour dots. So contour dots essentially tell us the interfacing between things. And it looks to be fine, but it's maybe not the best, so just go back to phenylalanine for now. Oh. Okay, I think that's a little bit better for now. Yeah, definitely we want to go through the map and fix all these green and red spaces to minimize the R factor and R free values as much as possible. This rotododecahedron can be very useful for helping understand whether or not the rotamer fit is good. If we just went to edit, go to A, and then set residue number 1. Then we just press space through, and then all of the parts where it's green should be fine. But if something is orange or yellow, you can try to fix it a little. Oh, it's actually significantly better. And then, for example, we can fix this a little bit too. It's a little bit better. And fix this also, if you can try. You want to optimize the structure so that it fits the model or fits the electron data as best as possible. And this is part of solving a structure. Also, for here, we don't actually see the electron density, which is slightly concerning, you can say, but you can sort of try seeing it by scrolling up a little bit more, by saying control and scroll. But generally, I think it's fine for now. In the real world, if you really wanted to dig really deep into this and figure out exactly which amino acids are supposed to be there, you can do so by obtaining the sequence and then double checking and say, okay, this is number 12, residue number 12. Does the sequence say residue number 12 is a glutamic acid? And if it says yes, then we definitely have to keep it that way. If it says no, then you can go ahead and fix it to the actual residue identity. That will be something that we'll do for our projects. This is one part of the process. Manually refining and then feeding it back into auto refine in the other programs that we'll be introducing. So say, for example, if you had enough of validating everything as much as possible, and say, for example, all of your ligands and everything seem to be fine, what we do want to do is go back to this unmodeled blob. We see this humongous blob over here that's just sitting here. This is that ligand. This is that inhibitor interacting with this protein. So let's go to that and say get monomer and say LZA. This is the identifier for that ligand specifically. And okay, what we're going to do is we see that here. We're going to hide that for now. And we go to ligand, find ligand, and we say search right here because I know that the pocket is already right here. Let's just say find. And then this will show us what it looks like in the pocket. Okay, it looks moderately good, except for the fact that this is like outside of the pocket. So then we can say this to actually refine in. Okay, much, much better. I think that's actually very good. Let's just go ahead and merge this new part into our overall protein structure. Let's go ahead and merge that. Okay, very good. Let's close that. Very, very good. And so if we wanted to do more validation, this looks like a nice proline. So let's go ahead and mutate that to proline. There we go. Alrighty, more points. This is histidine. So we can go ahead and mutate that into a nice histidine. There we go. Okay, our first couple of things was first fix the backbone, then fix the side chains, add in blobs, add in water. Another blob for our unmodeled blob is just, this could be sulfate. Let's try adding a sulfate. You can just say sulfate directly, sulfate ion, and say okay. Did it work? Oh yeah. So then you can sort of let it jiggle around. And so that original one, I'm going to delete. So I just want to really go around and maximize our Moorhen points and thus also decrease the R-free and R-factor values. In the protein data bank, the published structure has R-factor of 0.24 and R-free of 0.20. We started out at around 0.27 or 0.28. This Coot process is very, very important because we have to do that iteratively with the other software to get closer and closer to a lower and lower R-free value. And so definitely, if we just go back to ligand, center on ligand. Here is our ligand. If we wanted to take a nice, pretty picture of this, then we can simply do the models, get rid of these guys, add in our ribbon. So you see our nice ribbon. We also want to change our preferences or change our view so that we can actually see our ligand better. For example, we can make this front clip more back fog here. That's, for example, that's good. You can see what is this interacting with? This is interacting with forming hydrogen bonds and more hydrogen bonds. Especially over here, hydrogen bond here, and also just surface contacts. And so it's largely interacting with the backbone hydrogen bond sources on the protein. this inhibitor. And that could potentially influence the ability for the protein to form tertiary structure. This is one example of how we can see at the atomic level how a ligand is interacting with the protein for therapeutics. And for this specific case, it's interacting through hydrogen bonds in a protein pocket. Now that you guys understand the basics, or begin to understand the basics of solving structures, I challenge you to get a R-free value less than 2.3 and Moorhen points over 1,800. So you can get the structure as close to the model as possible. Good luck.